Recording's rolling. It's Wednesday, October 22nd. And I don't get to do too many gigs with you guys, so we're gonna put off this lab until we'll use this as a review lab next semester. So open up a little bit more time. Yeah, so we'll do it here on circular motion. I picked out a few textbook puzzles from chapter 6, so see how that pieces out by the end of class. The rest of the week, I have we'll probably do more textbook puzzles. I'll have you guys turn these in on Friday. And then what we were doing class here, you guys credit for. I also have a couple of our keys picked out, so that'll be good. I'll get you guys your take-home quiz by end of class today, and let's have it due on Monday. All right. So, you guys ready for Kahoot? Kahoot. Let's find out. Oh yeah! Look at you guys ready for Kahoot. You guys ready for circular motion? Hey, we're gonna find out who knows how to circular motion. Which one of these will be the winner? Circular motion.
Probably.
Which has greater linear speed on a merry-go-round?
Thank you. I probably also got a wrong with
Yeah. Guys, first go to the outside. Okay.
We all did. We were all I'm tired with Justin. I like typing.
Hey, this is right here. Guys, these are all spinning around. Guys, the question was about linear speed. Suppose there's a cop out here. It's like, all right, I'm going to get somebody with my radar gun. It points it right at Lincoln. What does his radar gun show for Lincoln? Zero. 0 miles per hour, 0 meters per second. It's all the same. Zero, whatever unit. Suppose Roosevelt here is zero. Suppose he's going at like 30 miles an hour. Zero. How fast does Washington go on? 16 miles an hour because he's twice as far out. Isn't that true? If you're twice as far, let me find the poster. This is one right here. So how fast is your linear speed? It's just proportional to your distance from the center. Is that right? Oh God! Ooh, points on the board. Yeah, points. Which has greater rotational speed? Here's your.
I understand.
Also called angular speed.
We're gonna get it wrong somehow.
That's Greek letter omega. It's a curly W. Omega. Angular speed, rotational speed. Yeah, they're all the same. They're all the same. We'll show you guys that too. Guys, don't only spin coins make the same turns per time. Is that the same number of radians per second? Same number of revolutions per minute, you could also say. Different way to quantify that. Same degrees per second. Okay. Yeah, same. I got Lily, Damian, Reigns, Nicholas, Austin. Yes. Which is not unit of rotational speed. Yeah, meters per second. Okay, there you go. Because that's linear. You guys don't know all those other ones? Don't know all those other ones? Describes the current rotation per time. Hey guys, let's figure out for the Earth. Guys, how many degrees per hour does the Earth spin? 360 divided by 24. What is that? Is that 15 degrees every hour? Ooh, that's the angular speed of the Earth spinning on its axis. Got Nathaniel, Tristan, Davian, Austin, Orange. Wow. What's the direction of the force that acts on closing the spin cycle of a washing machine? It's spinning. That's not what centrifugal is. Centrifugal force always pulls us towards the center of the circle. Oh yeah. Oh yeah. Whirl the can on the string. The string breaks. The can will. The colors match. Which color? Which way? Which color?
I only one that they. Oh, and then fine, right?
Yeah, let's always go. Yeah. Yeah. Can't do a circular path. Alright. Alright. Ladybug, bottom of the tin can being whirled in a circle. The force on the bug, okay, specifically on the ladybug. Specifically on the ladybug. It's directly due to it's ladybugs on the can. Go in a circle. Zoom, 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 zoom.
I think the one that they.
Yeah, I think it would be a space colony. The acceleration at the rim is g, say 9.8 meters per second squared. But if you go halfway, right? So this guy feels like he's walking around on Earth ground. Oh, you know, I feel like I'm on Earth. And then, what about this guy? Huh.
What? Yeah,
Hey guys. Okay, so that is.
Why are you?
Guys, that's this one right here. This one right here. Right? So, guys, isn't there a normal force from the wall holding him in? By the way, that can actually also work for the ladybug question too. Like the tin can providing normal force, keep the ladybug in. But now these people walk around. Okay? And if you divide by their mass, you get the associated centripetal acceleration, which you can set this to 9.8 meters per second squared. I mean, I guess you can get the spinning at such a rate for some radius. This works out to 9.8 meters per second squared. What if you climb this ladder? You get to like right about here, right halfway to the center. Okay, so you're like, guys, if you have half the radial size, but the same spin rate, right? The whole thing's like just like a solid disk spinning. Wouldn't that be half the associated centripetal acceleration? Okay. So you would perceive half the artificial gravity. Yeah. Half G. Got Austin, Nicholas, Tristan, Damien Ray, Power H5. Centrifugal force is in quotation marks. Apparent reality to observers in a frame of reference that is what?
What? Did you pick the one that my game is first? Me too. I don't know. It sounds you guys pick yeah, no, I got the moment.
Yeah. Guys, all those other ones are inertial frame of guys. Inertial frame of reference means you're not accelerating, which could be constant velocity or it could be at rest, because in terms of physics, those are sort of identical situations. Okay. Guys, don't I always say the word centripetal? I almost never say the word centrifugal. Okay. Guys, AP frames everything in terms of an inertial frame of reference, so that's only centripetal. So from our camera point of view, as you see this flying around, there's the friction force is acting towards the center of the circle. Okay? Now, if you're on this rotating platform and you close your eyes, you might think there's an outward acting force. Right? That would be centrifugal, right? But there actually isn't. But that's just from your frame of reference. You perceive that to be the case. Nicholas, George K, Tristan, Damien Reigns, Power 12. Person weighs less at the equator than at the poles. Mostly why? So this would be a good one to calculate too. I wonder how much less you would weigh due to the answer. Okay, yeah. Right. So you guys are on the concept. Yeah. Stand on the North Pole, stand on the equator. It's a little bit of a difference. I wonder how much. I might calculate that with you guys after. After this Kahoot. Back around that one. As the rotational speed of a space habitat. Think of that O'Neill cylinder. The apparent weight of people inside. What? Yeah, increases. In fact, we can get a little more specific than that. Yeah, guys, increases how? Guys, suppose this was spinning twice as fast. So maybe it starts off like 1 radian per second. We double that to 2 radian per second. Guys, what has happened to the inherent weight of all these people by doubling the omega? Increased by a factor of four. Guys, if you throw a factor of 2 on this omega, what's 2 squared? 4. Right. How about this? Guys, what if it spins 3 times as fast? They feel 9 times as heavy. Yeah. Lily C, Tristan, Nathaniel J, George K, Power H Bomb. Car travels in a circle with constant speed. The net force on the car? Whether it's a flat road or it's a banked road, the answer is the same.
Not.
Directed inward. Yeah, it's directed inward. I'm gonna find a picture here. They find where's my car going around? Okay, well, here's one of them. Here's the car on the bank track. And back a few weeks ago, I showed you guys on a flat track there was a friction force that was allowing you to turn. But here, there doesn't even need to be any friction. Okay, guys, here's the net force right here. Here's the net force, F net. You guys see how it's pointing to the left? Right, if I break this normal force into components, it's pointing to the left. Hey, which would be the center of this larger circle. Okay, so here's the radius of the circle right here. Yes. Directly toward the center. Got Tristan, George, Lily, Nathaniel, Power H Bomb. Space colony. What is the apparent gravity along the axis of rotation?
Right. You say.
Yeah, zero G. Okay, kind of back that up with the formula. See if I can back that up with the formula. So, guys, if this R is 0, it doesn't matter how fast it's spinning. This would be 0. 0. Yeah. Okay, 4 points. Smart.
I'm getting my 5 on my 8.
Conical pendulum shown. What force keeps the ball in its circular path?
Why is it gonna be a ball on here? Oh, okay. Thank you. Anyway, I mean, really, it was my fault. I mean, I would like to offer this myself.
Yeah, the horizontal component of the tension in the string. Oh yeah.
I would have said that.
So you guys remember this? Okay, so here's the ball here. 2 forces, weight down and tension force. Guys, which force is bigger? The weight down or the tension force at an angle? The tension force is bigger because it has to do 2 things. It has to hold the ball against its own weight, and it also has to pull it in, providing this net force, which is the centrifugal force. Yeah, gotta do all that. Boarding. Schwab, Lily, Tristan, Power Schwab, Nathaniel, on fire. You ride a motorcycle in the opposite direction of the spin of a space colony. Okay. Help you guys out here. Okay, so let's take things to extreme. I'll give you guys a very specific example. Guys, what if the whole colony is rotating, let's say, clockwise at 1 radian per second? And what if this guy, let's turn speed to an angular type speed, is going counterclockwise at 1 radian per second? What is he doing relative to the camera? And maybe we're in our own space station because we got our own camera and we're watching them kind of in the distance, right? Okay. So this whole colony is rotating clockwise 1 radian per second. This guy's going counterclockwise 1 radian per second. What is he doing relative to us? Not moving anywhere. Right? So then what? See if you can figure out from there.
Wow. You feel the silence.
Yeah, yeah. All right. So the general answer is feel lighter. Okay. In that specific case I gave you is an extreme case that it guys if he's just kind of sitting there just floating around relative to someone else that's floating around space like us with the camera, okay, they might just kind of drift off. Yeah, yeah. He would actually feel zero weight for that specific example I gave you. Okay. Got Lily, Austin, Kristen, Orange Ball, Nathaniel. Rotational speed of a wheel is defined as rotations per unit time. Rotational speed.
Oh no. No, I thought that would be more. You got to make it.
Yeah, true.
It would have been right.
How about radians per second, revolutions per minute?
I didn't click it.
Austin, Lily, Tristan, Orange Ball, Nathaniel, back on fire.
It didn't click it.
Space colony can be rotated so that 9.8 meters per second squared is felt at the outer rim. Yeah, you totally could. Okay, so that would be. Let's go back to where are you? Ah, here it is. Guys, suppose you know this is like 3 kilometers, and you want to target 9.8 meters per second squared for all these people walking around right here. Okay. Could you calculate exactly how fast to rotate it, right? And how much time it would take to go around? Yeah, so you could do that in principle, right? That'd be a pretty good one to solve. But I'll that here too. Okay. Yeah, I might round back to that one too, maybe. Right? Got Damian Rains, Austin, Crispin, Porchwall, Nathaniel. Only reason that riders on a carnival ride don't fall out is because they are strapped in. Okay, like that type picture. Okay. Yes. All right. Guys, what force is actually holding them in place? Huh? Friction. Yeah, friction. Here, actually, let's go and mock up the quick free body diagram. Actually, this might not be a bad picture to think about. Guys, if here, let's look at this person right here. Put a free body diagram on it. Guys, on your free body diagrams, you guys are definitely using rulers on your free body diagram vectors, aren't you? Yeah. What force is trying to make them slide straight down? At his own weight, mg. What force is guys, what force is pushing out this way? Yeah, this is the normal force pushing towards the center of the circle. Right, can you guys think 3D? I'm doing 3D, right? Can you guys imagine 3D? Right, this is the center of the circle right here. Here's the center of the circle. Like, shoot, going around. Okay. And what force is holding him up? Friction. Yeah. As normal is perpendicular to the surface. The surface is vertical at this time. So the normal force is straight towards the center of the circle, horizontal. The friction force is perpendicular. What if he's like, hey, I want to get this carnival ride. I'm going to wear the slipperiest clothes that I have, and I'm covered in wax paper. Spin me up. What is this friction force? Guess what this guy does? Kristen, Jamie Rains, Austin, Porchball, Nathaniel. Bug on a phonograph record will make more turns per minute if it moves towards the center.
The second one.
Guys, what happens to your angular speed if you change your radial distance? No. Nothing. You still make the same turns per time. It doesn't matter where you're standing. Here, let me show you guys. Don't all these make the same turns per time? You guys see that? Same turns per time. Same turns per time. Lily, C, Damian Reigns, Austin, Porchball, Nathaniel J. You whirl a can on a string. The tension in the string provides the centripetal force to keep the can in a circle. Yeah, basically true. Okay. Here's maybe kind of an exception to this. Because if AP asks that exact question, then they give you this picture where there's definitely like this angle is definitely not 90 degrees because realistically this is the answer they'd be looking for is the horizontal component of the tension. Okay. So if you were thinking like that, then that's actually might be a little bit better. Okay, but basically true. Also for the lab you guys did with the Play-Doh canisters, you were assuming that was the case. Okay, the full tension. Lily C on fire, Damian Reigns, Porridge Ball, Austin, Nathaniel J. Oh, is this for the win? I think it's the last question. For the win. Who will win? Kahoot. Ladybug on the inside of a spinning bike tire can't experience a force that feels like gravity. So put the ladybug in the tire. Throw it off a cliff. Spinning. It's spinning. Yeah. All right. Let's go. Yeah, it's just basically an O'Neill cylinder, isn't it? All right, with the bronze, Porridge Ball. With the silver, Austin. And the gold, Nathaniel J. Oh, yeah. Oh, yeah. All right, nice job. So, guys, there were a couple of questions there that I do want to solve with you guys. All right, so one of them is that your weight on the equator question. Let's just. So you guys write in your notes. Let's solve what is your weight at the equator compared to at the pole. So we got a guy standing here, a guy standing here. Say how much less do you weigh at the equator due to Earth rotation? Okay, you guys get the idea, right? So if you stand on the pole on a vacuum scale, you reach some weight. Right, then you stand on the equator, and the whole Earth is spinning. Ooh, it's spinning. Got some angular velocity going on. So I think you weigh a little less, right? Because what if the Earth is spinning really, really fast? Do you think if it's spinning so fast, you might eventually like fly off the surface? Yeah. Yeah, if it's spinning fast enough, in fact, at that point, the whole planet would just kind of break apart and crumble. But I wonder what that would be. So check that out. Let's see some things. I'm gonna give you guys a mass of let's say 50 kilograms. Okay. And I'll call regular Earth gravity. Okay, let's go 9.8 today. 9.8 meters per second squared. Like that. Okay. So what would your weight at the North Pole be? Could it just be just multiply those two together? Is that right? Okay. So 50 times 9.8. I'm looking at 490. What's the units? Okay. Okay. So that's at the pole. All right. So that's like our baseline values. Okay. Now I want to know for this guy on the equator. So let's go to the equator. Let's say equator. Let's look at the surface. All right. So this guy's on a curved surface. Definitely kind of exaggerating here. Put a guy right here. Okay. And the fact that he's on a curved surface is the true net. Even if he's standing and he said, "Oh, I feel like I'm at rest relative to the surface there." Is he in true equilibrium? The fact that he's moving on a curved surface? Not quite. Not quite. Okay. So let's do a free body diagram. What force is pulling him straight down? Yeah, mg. Mg. Okay. And actually, would that basically be 490 newtons? Okay. Now, in truth, the radius does bulge a little bit at the equator, but we're going to call it 490 newtons. Okay. So that's 490 newtons. Okay. But let's say you stand on the scale right here. Standing on a scale. Okay. The scale reads actually what kind of force? The normal force, F sub n. Okay. And actually, that's what we're trying to find. We're trying to find the normal force. Okay. Now, guys, these two forces conspire together. Do they sort of subtract from each other? Because opposite directions. Okay. So do they sum to zero?
Not quite.
Not. Yeah, not quite, because he's moving on a circular path. We haven't quite considered this up until just recently here.
Yeah.
There is some more information. There's at least one other number I can think that I do have to give you to solve this, and there's some kind of set you have to do. But maybe I'll probe you guys. Right, so let you guys this far. Right. What's something you guys think you can do next? Either a set you can do, or maybe a number you need that I haven't given you yet. Which would be what?
I don't read.
Radius. Yeah, radius of the Earth. All right. Yeah, so you do need that. So I'll give you guys the radius of the Earth is 6.38 times 10 to the 6 meters. That's like 6 million meters. Okay. Yeah, you do need that. Okay. What else can you guys think? Yeah.
Maybe like the speed of the Earth rotating.
Oh, yeah, speed of the Earth rotating. Let's do that too. Right, so let's go omega. How about that? Let's go omega. Okay. Guys, what is omega for the Earth?
Great.
One revolution every 24 hours. Actually, maybe one rotation, I should say. Normal revolution is like you're going around something. Rotation is like spinning on your own axis. Yeah. You guys get the idea. Every 24 hours. Right. If I want to do math with this, because it looks like I'm looking for a mathematical type answer. Yeah, I better not have revolutions per hour. I better have what per what? Radians per second. So how many radians in a revolution? 2 pi. Yeah, 2 pi. There's 2 pi rad in a rev. And then, well, here, I'll just do 1 hour is equal to how many seconds? Yeah, 3,600 seconds. Right, because 60 times 60, right? Yeah, so let's get the angular velocity here in radians per second. So 2 pi over, and then in parentheses, I got a 24 and a 3,600. Okay, guys, I'm going to get a tiny, tiny number here. This is 0.0000727. I'll just cut it off there at radians per second. Okay. All right, so that might be a good number to know. Okay. Because if the Earth was spinning faster, I think this guy's scale rating would decrease. You guys can kind of imagine that. All right. So yeah, you guys make a good headway. You say, okay, well, you would have to know the radius of the Earth and how fast the Earth is rotating, and we have those values now in base SI units, so we can do math with them. Right? What's the next thing you can do? Remember, our ultimate goal is to figure out what is the scale rating. Centripetal force. Okay, guys, what's a formula that you guys know for centripetal? Okay, yeah, here I can think of a couple.
M omega squared.
Yeah, you could also do this one, M omega squared R. Okay. Now, which one do you doesn't make any difference? It's the same numerical value. Since we have omega, I'll just go ahead and run with that. Okay. Although you can quickly convert to the just multiply by multiply by R. But okay, let's use this one right here. So centripetal force must be for your mass. I'll put 50 kilograms. Omega. Well, we just got that. Actually, I should have you guys put that in scientific notation. Could you guys put that in scientific notation if you wanted? Yeah. Is that here? Oh, right here. So it's 7.27 times 10 to the what? -5. There you go. All right. So 52. All right. So let's get what is the necessary centripetal force? 50 times 10 squared. 48 times 10 to the 6. You guys get what I'm getting? About that many newtons. Are you guys getting? So what does that mean?
He's 1.6 times. It means he's getting pulled towards the center at that much newtons. So
yeah, that is the net force on the sky. Okay. Actually, does that answer the question how I phrased it? How much less do you weigh at the equator compared to? Yeah, actually, that's the answer right there. Right. He weighs almost 2 newtons less. No, 2 newtons. Because here's a 2 Newton weight right here. Okay. So if you're standing on the equator, and let's say the Earth was not spinning, you weigh some amount. And if you have the Earth spinning at what it's actually doing, you sort of weigh less on the scale by this much due to the spin of the Earth. Yeah. Right. Okay, we sit here. All right. I wonder what is that? So what would the scale reading then be? Because guys, it goes like this: net force is his weight pulling down minus the normal force from the scale up, would that be the net force? And the net force is the centripetal force. So I got 1.68 set. So I guess I'm chasing out a different question, which is what is the scale reading? What's the scale reading? That's this normal force right here, isn't it? Scale reading. So add, subtract. So what's 490 minus the answer? Yeah, 488 newtons. Okay. So Earth is actually pulling down on him with 490 newtons, but the scale only shows 488. Ooh, because the Earth is spinning. Ah.
I need to stay on it.
I wonder. I wonder how fast, guys. How fast would the Earth have to spin so that this guy's weight reading on the scale goes all the way down to zero? He starts floating off into space. Huh? Can you guys think of a way to solve that?
No.
How?
You said you have to do it like you use the Fnet equals mg minus Fn and you try to like set Fn is 0. Is that it?
Yes. Yeah, guys. Set this equal to zero. Wouldn't that be the centripetal force here, which could be it could either be mv squared over r m omega squared times r, the centripetal force, just equals mg, right? Something like that. And also, there's actually a variation on something that we did already. Digging it up here. Where is it? Ah, here it is. Here it is. Guys, wouldn't that be this right here, basically? Centripetal force provided by weight. But here's your mg, but here's the universal form of it. Here's your centripetal force, mv squared over r, and you could solve for this one you're solving for like orbital speed. Okay. Do you guys know how much time it takes a satellite to go all the way around the Earth? Yeah, 90 minutes. Aha, 90 minutes. Yeah, yeah. Okay. Could you go distance equals speed times time? And the distance around the Earth is the circumference, 2 pi r. I told you r. Okay. And speed could be this value here. I think it's like 7,900 something meters per second. You can solve for time. Yeah, it should work out to like 90 minutes when you convert to minutes. That. And in that Kahoot, there was another question I want to ask you guys, which is let's make an O'Neill cylinder. O'Neill cylinder.
Sometimes it's mg minus 2. Because of course it is.
Oh, I wonder how fast would you have to spin this O'Neill cylinder about its central axis? Okay, what is this omega right here? So that this guy feels Earth gravity of 9.8 meters per second squared. Okay. Oh. But to answer that question, you have to know what is this radius right here. So, here, let's come up with a random number. 19. Let's go 19 kilometers. 19 kilometers. So let's say radius is 19 kilometers. Guys, how many meters is that? 19,000 meters? Something like that? So we got to do something. Okay. Right, so how fast is rotation to feel G artificial equals 9.8 meters per second squared? Guys, what's a formula you guys can think for that? Guys, if you're solving for omega, it should probably have a. Oh, when you say how fast is the rotation, is this referring to omega? Okay. Yeah, now, guys, 9.8 meters per second squared. Is that a force or an acceleration? So do I want m omega squared r, or do I just want omega squared r?
Omega squared r.
Yeah, let's go with that one. Okay. And that should be equal to what? 9.8 meters per second squared. Okay. And this radius here, actually, right there. So omega, would that just be square root of g over r? Okay, so that. Okay. Go ahead, solve that.
G over R. Oh.
So okay, square root 9.8 over 19,000. Did you guys get 0.0227 radians per second? Okay, you guys got that? Okay. I wonder how much time it would take for this whole thing to go around once, make one revolution. Here, let's do a railroad track set for this, right? So one revolution. You also do a formula version of this. Okay. Yes, one revolution is how many radians again? 2 pi. And every 1 radian, could that be 0.0227? Whoops, sorry, that's wrong. Whoops. It is 0.0227 radians every 1 second. Okay. Now I think this is probably going to be a lot of seconds. So, do you think that maybe more reasonable? I mean, this is a huge O'Neill cylinder. Do you think maybe I should put this in minutes? Maybe. Okay, let's put it in minutes. I'm guessing. How many seconds in a minute? 60 seconds, 1 minute. Let's try this out. Let's see what we get. 2 pi divided by, and then parentheses 0.0227, 60. Yeah, 4.6 minutes. Okay. So if there was this particular O'Neill cylinder in space, you would want it to rotate in about 4.5 minutes. Okay, and that would give you the artificial gravity surface that was occur. Okay. Here, I got a Tom Scott video for you guys. Well, it's part of this. Okay. He's in this rotating room. So that whole room is rotating. Okay. It's kind of like O'Neill cylinder. You guys, oh, there it is. There it is. You guys see that? You guys see that? See it rotating? Okay. Now, this is small enough, has small enough radius that you don't really want to walk around inside because then you'll perceive there's this weird Coriolis effect. You know, I don't think I ever showed you guys the Coriolis video. Fine. I'm going to dig that up while you guys are watching that. Videos. Rotation. Coriolis. Here's my Coriolis. Stop that. Okay, so do you guys see from our point of view? Whoops. If I go back to the beginning, see, we're up in a helicopter, and from our inertial frame of reference, you guys see that yellow ball is pretty much going in a straight line. Straight line, Newton's first law of motion, straight line. But on the surface, it looks all wonky like that. Yeah. Okay. The same thing, when you get in a spinning room, the physics all goes wackadoodle. Yeah. That ball's going in a straight line, you guys know, right? All those balls are going in a straight line. That's just Coriolis. Okay. But if you have an O'Neill cylinder that's big enough, then that'd be a really oh, come on, give me my camera. Okay. That'd be a really subtle effect. So this one you might be able to actually walk around, and it might be hard to tell that you're not under. Alright, what do I got here? Alright, so I picked a couple that are circular motion and also some that are gravitation, but we'll see how much we can do by the end of class. So number 9, a coin has mass 25 grams. It rests on a horizontal record player's turntable that rotates at 78 RPM. Guys, what does RPM stand for? Yeah, revolutions per minute. The center of the coin is 12 centimeters from the turntable axis. The coin does not slip. What is the minimum value of coefficient of static friction between the coin and turntable surface? Isn't that this right here? Right. I'm gonna find out. Who knows how to actually do this? So I'll draw the situation. We got this turntable. All right, so I'm thinking in 3D. We got this axis of rotation. I'll give you omega exactly as they gave it to you, which is 78 revolutions per minute. They told you that this coin is 12 centimeters from the center. Okay. So this radius right here, R equals 12 centimeters. And they told you that the mass of this coin is 25 grams. Okay. All right, so find mu sub s, coefficient of static friction, minimum. Okay. Because of course it could be larger than the necessary value, but it just can't be less than some value. Okay. All right. All right, so walk through this with you guys. What's one thing that you guys think we should do? Here's one thing then right off the bat. Let's look at all those three given values. All those three given values.
They're not.
Yeah, let's put them in base SI units. Okay, let's do that. Also, I think you might need gravity field. Do you guys think that too?
Yeah.
So here, I'll go over here. I'll say omega equals. So we got the 78 revolutions per minute. Set of railroad tracks. Okay, so what's the next step? One revolution is how many? What?
2 pi.
Yeah, 2 pi radians. Okay. Okay. And ooh, I don't want minutes. I want what? Seconds. So 1 minute is 60 seconds.
It's
78
Oh, yeah.
Yeah.
2 pi over 60.
You remember which one?
8.168.
Remember when it was like
Radius
regular?
Okay, then how about mass
Now we're talking.
could be 0.2 no 0.025 kilograms, and radius equals 0.12 meters. Okay. And let's use G equals about 10 meters per second squared. Okay. Okay, so we'll start off with these given values right here.
Where's
The minimum necessary coefficient of static friction. So coefficient of static friction. Right. What's next? What should I do next? Yeah, okay. If I'm solving for a minimum, yeah, maybe I could set equalities, okay. Yeah, okay, so I like that, but let's do that. So I think that the friction force is acting and not the centripetal force, isn't that true? Ooh, yeah, you could take the centripetal force. Yeah, let's do that. M omega squared times R, right? And what can you substitute for friction force? Yeah, coefficient of friction times the normal force. Is that right? Okay. Yeah, you also said inequality, but I'll leave that as equals just because we're solving for the minimum necessary value. So it's really the minimum necessary value. Okay. What next? Maybe I should have drawn a free body diagram on this coin. Okay. Because what's one force on this coin?
Isn't the normal force?
Yeah. It's weight, normal force. Okay, so mg, f sub n, and also
How did you get that back?
also this friction force that always points towards the center. Okay. Yeah. No, so what'd you say next?
Substitute.
Yeah, this normal force is equal to this mg. Ah, math cancels out. I like that. Yeah. Oh, it looks like we're solving in terms of variables. Let's get practice. Anyway. Actually, no, we're one step away from just getting in terms of variables. Yeah, divide by G. So your coefficient of static friction is that. Hey, that looks like the poster, doesn't it? Yeah. Oh, yeah.
And then we drew.
Yeah. Plug some numbers in. So, and we have all the base SI values of the numbers right here. So let's go 8.168 radians per second. I'm going to square that. Multiply by a radius of 0.12 meters. Then gravity field.
The Rubik's cubes don't change on me.
So, see if I mess it up with it.
Ah, are you guys getting this?
Oh, I
Oh, what unit? No. No unit. Produce. This is one of the numbers you can just use be a number. It's the ratio of two forces. Yeah, that's it. Alright, guys, ready? Alright, well, we got 2 minutes to the bell, so I will put this take-home quiz in your guys' hands, and that'll have to be a wrap on today. More adventuring tomorrow.